morning. Welcome to the Machine Learning and Artificial Intelligence for Data Science course. Last week we talked about clustering, an unsupervised methodology to group together data across multiple dimensions. And we started with k-means. We show that this is a relatively simple but powerful algorithm that help us to cluster together high-dimensional points. But we also saw that it suffers for some limitations. So it is used quite a lot in practice, but we saw that when it has to address clusters which have different, they come from different distributions, they have different variants, for example, or clusters which they have different variants across dimensions, then it doesn't work well. We talk about the fact that is when we have non-linear embeddings, it also is limited, and we show a trick on how we can extend k-means to kernel k-means to improve that. And then we went to mixture models, so we covered quite a lot of ground. So I want to repeat a couple of elements from mixture models in order to ensure this is well understood. So we said that mixture models is a completely different perspective of how to do clustering than k-means. It's a generative model. So what it does, it tries to reverse the problem, to apply reverse engineering. So instead of starting from the data and thinking, okay, I will cluster them based on some kind of distance from each other, they start from where the data comes from. So instead, they try to model this process, to model this distribution, so to model the generative process as distributions. And a common distribution that we use in practice is a Gaussian distribution. Because a lot of phenomenon in practice, they do follow a Gaussian distribution. So a Gaussian distribution has a mean and a variance. It gives us a lot of flexibility compared to k-means, because that means the variance can change across different dimensions. That means that we can have completely different distributions across clusters. And it also means that we can have a soft assignment. So a point doesn't have to belong to one cluster only. It can have a membership. It can belong more than one cluster. And why this is useful? This is useful in practice because it allows us to describe those points, their membership, in terms of the confidence as well we have. So there might be points that we are very confident that belong to one cluster over the other, and other points that we're not very confident, and this membership reflects that. And then we started talking about Gaussian distributions because these are the tools that will help us to solve the problem, to help us to assign memberships to each of the points we have. So we try to guess these Gaussian distributions from the data. And we show those distributions in the simple form in 2D. Then we said, okay, they don't have to be 2D, they can be 3D, and they can be multi-dimensional as well. We restricted ourselves to 2 dimensions here to make our problem easier for the visualization. And we saw a few examples. And then we talk also about the distributions, the Gaussian distribution themselves, like why the covariance, the sigma, is important here. And we saw that the sigma can, depending on how we parameterize the sigma, it can describe more complex distributions. Even in the simple form, when we have, for example, a Gaussian distribution described with variance which is 1 across across your covariance matrix, you see that this resembles the k-means. So it goes back to the k-mean, as we said before. But we can have, we can still have different clusters, different Gaussians that we try to extract, that not necessarily all of them, they follow this simplistic form. And then we said, okay, so how we're going to assign these probabilities to each point? And we got down to thinking probabilistically, how we can think now probabilistically and go back to the points and say, okay, what is the likelihood of this point here to belong to cluster A or cluster B or cluster C? Effectively, what is the probability of this point to belong to a Gaussian A or Gaussian B or Gaussian C? And and by considering here the likelihood, and what this likelihood of the data point is, given that it belongs to component K. So effectively, we assume that we have 3 or 4 or k Gaussian distributions in our data, and then we go to each of the points and we ask the question, okay, based on the characteristic of this Gaussian, what is the probability we have what is the likelihood of this point to belong to each of those Gaussians? And this is the problem we try to solve. So we said that we have priors. So even before we start looking the data themselves, we have a feeling of, with the probabilistic tools, we need to assign a prior that tells us what is the frequency of generally on the data to belong to X cluster or to A cluster or to B cluster. So that's what the prior shows. So is a feeling we have before we can even start solving the problem of how many points would belong to a Gaussian A or Gaussian B or Gaussian C. But effectively what we want to solve is we want to have a soft assignment. We want to estimate the probability to assign data to each component. So we can see here the equation of this, what we see on one part of the equation is exactly the probability of this point to belong to what is the probability of a point to belong to a specific Gaussian cluster, given the characteristics of this Gaussian probability. And then here we just see a normalization, because we know probabilities, they have to sum to 1. So effectively we need to normalize for that. And then we talk about, okay, the way to solve that we have is an iterative way. So it's the expectation maximization algorithm. And the expectation maximization algorithm remind us a little bit the k-means algorithm. So it has similar steps. Again, it's iterative. Again, it has properties that allows the algorithm to converge. So we say, okay, we have to guess the number of clusters. We knew that. We have also to guess the parameters of those clusters. So effectively, you have to guess the parameters of our Gaussian distribution and the prior with relation to our data. A guess of how often we have data belonging to one cluster or to the other. And then we compute through the expectation step our soft assignments, and we update those steps similar to what we've done. We update the parameters of the distributions again, and we repeat the same again over and over, like we did with k-means, until those parameters they don't change anymore. So that's what we covered last week, and we stop here. So here is just an example, a visual example of how what that means in practice when we apply this generative way of thinking for clustering. So we see here we have cloud points, and we don't know where they belong. We have make a guess that we have 3 clusters. You can see that those are Gaussian clusters. They can be modeled with Gaussians. You can see that they are different with each other. They have different means because they're in different positions, and they have different variants as well. So you can see that this cluster is more concentrated. The others are more spread. So they have different variants. And as we iterate, we update the membership, the probability, the soft assignment of each point to belong to each of those clusters. So we can see that the first few rounds, those parameters change dramatically, but then they start converging. Converging based, of course, on the properties of the data. And when we don't have any changes, then we said, okay, now the algorithm has converged, and we have the optimum solution for this problem based on the initial guess we've done for the number of clusters. So now we've got the parameters, but we still need to decide about the assignment. So now what we have estimated, we estimated our Gaussian, and we have the likelihood of each point with relation to these Gaussians. And we have a lot of options. We have more options than k-means. So in k-means, as we said before, the membership was, it was a hard membership. Either a point was belonging to a cluster or not. So here with the mixture model, since we have a membership, we can also decide which threshold we want to set. Do we want to go back and have a hard assignment by setting a threshold, for example, or do we actually want to keep operating with these soft probabilities? Effectively, in the end, we can still choose a hard assignment, as I said, and we can assign to the cluster, we assign points to the cluster with the highest membership value, the highest probability value here. So we come back now again to the same problem we had with the k-means, when we said, okay, how do we choose the number of clusters? So what happens when we increase the number of clusters, for example? And you can see here an example of how of having these 10 clusters starting as an initial guess for our problem. So we need to be careful how to find the number of the clusters in a data-driven way. Because what we see here is that if we add more clusters, in fact, the likelihood always increases. And the reason is because those clusters, they overfit to our data. So what that means? So that means is they create small neighbors and they can explain the data, but effectively, when you start using new data, then the error they produce is high. So they overfit so much, they kind of memorize the data, but they don't learn appropriately the generative process. So we want to avoid that. And our strategy to do that is with k-fold cross-validation. So I assume you heard a bit of cross-validation in the previous lectures, but I'm going to repeat the idea here. So the problem of overfitting or underfitting is in fact across most of the machine learning problems we try to solve. And cross-validation is a robust way to help us not only evaluate how well the model is, but also to help us develop the model, so to help us decide of which parameters we should choose in order to come up with the best model while we train it. So how it does that? It takes the data set we have and it splits it to folds, k-folds. Typically 10 folds cross-validation is very common for the data we have most of the times at hand. And it takes those 9 folds and it does a training based on those 9 folds. And then you use the remaining fold, the 10-fold for testing. And you do that, you go across all these folds. So effectively, you have 10 opportunities to test your algorithm. You're going to have 10 errors. So why it helps you? Because it helps you in that case to avoid overfitting. So even if, because if you start increasing your number of clusters, we know on the training data what you're going to do is you're going to create more clusters that they fit very, very well locally, but effectively those clusters, they don't really represent the generative process. They just locally fit the error you have there. So once you start putting more points, testing points, then you will realize that your models fall apart. So they cannot generalize. And the way to control that is by doing the cross-validation. So if you do the cross-validation and then look the log likelihood in the held out partition of your data, then you would be able to plot that across the numbers of clusters you have chosen. And then you will have an objective way to decide what is the optimum number of clusters for your data set. And that can guide you also in the development of your model. So we said before that we actually use Gaussian probabilities for our mixture models. But the fact that mixtures models are such a powerful way is it comes also from the fact that we can use other distributions as well. So Gaussians are very common because they have nice properties, because they are flexible, they are neither too simple, not very complex. But it's not only, they're not the only distributions we can use. We can use other distributions, and that gives us now a framework to model very different phenomenon and being able to cluster data that they come from different processes. And here I show you another example where we actually have the data comes from a binary distribution. So in that sense, we don't really need any more a Gaussian distribution. The data come from a binary distribution. And you can think that like similar to when you have a coin and you throw the coin and you make a probability distribution to reflect the probability of that coin to come from one side or from the other. And this probability, effectively what we see here, is going to be modeled by Bernoulli distribution. So we know that if we have a coin and we try to figure out what is the probability from one side or the other side, it's a binary problem. Effectively, the probability to have heads would be 1 minus the probability of having the other side. And each time you repeat, those are independent events. And since they are independent events, we can multiply their probability to figure out what is the likelihood of a specific point to belong to a cluster. And here again you see that the tools to estimate the parameters of this probability are similar to the tools we had for the Gaussian probability. But of course, what we have here is that we have flexibility in order to process the data. Either they come from bioinformatics and so on, that they have different properties than a Gaussian distribution. And that's just applying this distribution, and this is just to show you how this would apply in a specific problem where you actually the generative process it does come from a binary distribution. It can be explained better from a binary distribution. So summarizing, we introduced 2 clustering methods. We talk about k-means, intuitive way of clustering points, very powerful, used a lot in practice to give us an initial idea of our data, of how stable our clusters could be. We show that it can be kernelized to solve nonlinear embeddings and to help us cluster more complex problems. But we also see that it's limited in a number of other ways as well. And we introduce mixture model, which is a completely different way of thinking of different way of reverse engineering the problem, so that we try instead to guess the generative process of the data and not just cluster them based on a distance. But both of them are, we saw that are iterative schemes, that they converge, they don't have analytical solution. the mixture models, they give us a lot of flexibility. So we have more parameters now we can fit compared to the k-means. We have soft assignment, and we can even have completely different distributions that we can use to model our data. Okay. I'm trying to set up a Mentimeter, but for some reason it doesn't want to go. There's no way to drag it. Let me try another way. If you do have questions, so if you do have questions in the class, you can use a Mentimeter to actually shoot the questions. I might be able to answer a couple of them, and then some more during the end. Now the problem is that I can't drag the page over, so I can only present through PowerPoint. So you can take a picture of that now, because it's going to disappear. For the exams, and I have one question about any news in regards to the exams date. Let's discuss that at the end. So basically, there are no news about the exams date. That's something normally defined from our teaching team, so I haven't heard from that, but we're going to talk about the assignment more later on. So that's what I mean on that. Okay, so I take it not many questions about And by the way, since you're also here, screen. And this is the passcode, before I forget, for your attendance as well. You can put a note on that. Okay, let's go now to the next half, which is about feature selection and projection, and that's also unsupervised method, and very, very important, and we're going to discuss why is that. Let's consider a problem which will try to build a classifier that can diagnose leukemia. We use gene expression data, and a characteristic of gene expression data is that they are complex, multidimensional data, so they have a lot of features. And we can see that here, for example, we have 27 healthy samples. So we have data from 27 people that are healthy and 11 people that they have leukemia. So we have a total of 38 data. And each sample is the expression activity level for 3,751 genes. So we are talking now of thousands of dimensions you have to deal here in your classifier. So you have thousands of dimensions. You have only a few handful data sets, so you have only 38 data. And you try to build a classifier that is robust and is able to generalize the data on those data. So this problem becomes very, very difficult. It becomes difficult because of a very well-known problem in data science and machine learning, which is the case of dimensionality. So is the idea that is the fact, it's not just an idea, so it's the fact that if you add dimensions to your data, so if your data comes from a high dimensional space, then the samples you need needs to grow exponential the number of size of data you need to solve this problem. So this becomes computationally interactive very quickly, so it becomes very difficult to solve the problem. And in certain cases, you don't even have the data. So there are good reasons why it is important to, in fact, try to reduce the number of features. And before when we did the visualization, you saw visualizations with 2 features. Of course, we try to keep the visualization simple and intuitive. Sometimes we create more dimensions, but now we begin with 3,751 dimensions. So we need to reduce this number. And what we're going to see in this lecture is that we have two ways of reducing the number of features, the number of dimensions. One way is to do feature selection based on the original, so just use a subset of those features, and then, as we're going to see, we have to decide how to choose which features we can choose. And another method that we're going to also talk about it today is about combining those features, the original features, in a way that is efficient enough to tell us, to make combinations, to make powerful combinations. And then from those, select again the top features. So let's see this idea more. So let's go and see first the idea of choosing a subset. So going back to our original data, so we said that we had 37, 38 samples. Some of them are belonging to our normal class. Some others, they belong to the leukemia class. And we said we have this massive amount of number of features, which is 3,751 features. Okay, so how we're going to decide that each of those features, and you can see, for example, here the black outline, just select one of those features, whether we're going to choose it or not. Remember that this feature specifically has samples across both classes. So what we want to do is to make a way, to make an algorithm that can tell whether this specific feature can discriminate the two classes. So that's the problem we try to solve. So we try to discriminate whether those samples comes from a normal person or a patient with a healthy person, or a person that has leukemia. So what we do, we split those values that we have across this feature based on where they belong. Here we have two classes. There's a binary problem. Therefore, the features will split to two classes. And since we're going to have samples, and then once we split those features to the two classes, we'll estimate the mean and the standard deviation. And that would allow us to estimate a parameter, sigma, that tells us the significance of this feature by subtracting the means and dividing by the standard deviations. So now remember, where did you see, again, the mean and the sigma? You saw that when we talk about Gaussians. So we talk about Gaussians, and we said that they're not too complex, but they're also powerful and simple enough because they're described by a mean and a variance. And it's the same idea here. So this is different examples, different features. So these plots here represent different features. And the way we evaluate whether they are important or not. So if you, for example, look into the feature here, then what we see is that, okay, we went to that feature, across that feature, we split the data based on the class they belong. We estimated the mean of the corresponding class, and we divided by the sigma, we estimate a sigma, and we estimate a sigma here. The sigma here, though, we can see that the mean between one class and the other it's very small. Therefore, the sigma of this feature, the significance of this feature with relation to how well it classifies the data to healthy and people with leukemia, is very small. Because we see here the distribution of this feature. By looking at this feature, we have a lot of overlapping. So if we have a point in the middle, we don't know whether it belongs to one or to the other. But even if we go on the sides, the uncertainty is very high. Now we can see another feature. We can see here that the means now are more separated. And we expect that the significance of this feature with relation to this classification problem would be higher. We still have an overlap, but for most of the data we can decide whether we can have a high likelihood whether they belong to one or the other. And then we go to the third case, where we can see well-defined clusters here of our points. And we can see that the means are very well separated, and they also have a small variance, which means now we can decide based on this feature whether our samples belong to healthy or to the healthy population or to population with leukemia. So this is the underlying idea about selecting features. So we select features that they can tell us, they can give us, they give us a lot of information of whether our samples belong to one class, second class, third class, or so on. And then again here we have to decide, okay, now that by doing that, what we can do, we can order the features. So we can order the features based on this importance score. But how we choose how many of those we can take. And we can do the same ideas we choose before for the class. So we go back to the cross-validation, don't have any better way. So we go back to the cross-validation because it allows us to see how well those features we selected, they will generalize if we add new samples, if we test our error to new samples, to new patients. That's what we want to know. So again, we have to split the data into K-folds, C-folds, and do the same process where we select features based on C-1 fold, and then we test on the other fold. And that will give us again a curve where a curve that will show the performance of the classifier along the number of features we select. And based on that, we can decide how many features we can choose. Important when you do cross-validation is not to mix the testing and the training data, because that's a huge mistake in machine learning. It invalidates all your results. So you won't be able to trust your model. And you will need to start your experiment and your training and the development of the model from scratch. So here, to come back to our example, by choosing two features, so we choose, we can see and plotting those features across all samples, we can see already that they actually classify give us, they can classify what is healthy and what is unhealthy. So let's assume healthy is supposed to be the data points with more samples than unhealthy, which is also very common when you have data sets in healthcare to be unbalanced, which means you have more data from the healthy class, which is fortunate, and less data from people that are unhealthy. And this is exactly what we said before. So this is how we can decide, in this case, of what is the optimum number of features to choose. So we plot the testing error, not the training error, the testing error of your cross-validation results with relation to the number of features, starting from 2 features and so on. And hopefully that gives us an objective way to choose the number of features to select. And also, it gives us an idea that actually we don't need all those dimensions. And if you use, the interesting part of this is that if you use all the data that they have the information of those 2 features, then this makes the performance of your classifier far worse. And that's another evidence of the case of the dimensionality. So you do have all the information there. You have your 2 good features, and you have other thousands of features. But unfortunately, that doesn't help to make a robust classifier that is able to generalize to new data. So we covered now how we're gonna see, how we can select features from the original features, how we can create a subset. And now we're gonna try to think about another way of actually how to make new features. Because that's also a very powerful technique used in machine learning. So one way actually to create features is by using clustering. So you can use the techniques we learned before to reduce the dimensionality of your features, because the clusters effectively gives you this idea of I can describe my data based on the fact that they belong to a specific cluster. Therefore, why not using, for example, the parameters of my distribution as my new features now? So if I have clustered my points with 3 Gaussian distributions, perhaps you can use the parameters of the distribution as a way to make new dimensions, new features. And that's going to be a reasonable approximation of your data. So that we heard already. What we're going to hear now is about projection, which is another technique where you actually project your points to another space. But before we do, let's take a break, and we will we'll be back here at 11, so we can continue. let's make a start. So let's make a start. Talk about projection, which is another way for for reducing dimensionality in our feature space. So what is projection? Projection, you can think of it of how intuitively think about how projection when we, for example, have our hand in front of a light source, and you can see the shadow. So the shadow now is the projection of our hand. And you can think of it, that the projection can change if we change our angle, the angle of the hand with relation to the light. So the same idea is, we can apply the same idea with relation to our data. So we have our hand, which is three-dimensional, and we can project it to a two-dimensional space by looking just the shadow of the hand. And we can see later that this projection, the quality of the projection, depends on how we're going to turn our hand. So there are some projections that they will be better described, would be more easy to distinguish that we have a hand there, and there will be other projections that would be more difficult to tell what they are. So that's the intuition behind applying projection in our data to minimize the dimensions of our data. So how we do it in practice? So let's try to explain the problem now with our equations. So we want to project our data into a lower number of dimensions. So let's say our data are X. We want to find an array W, where we multiply with our data to produce a projected version of our data in a lower number of dimensions. So let's say our input array X is n by d dimensions. Then intuitively, we know that in order to multiply with another array, which is W, there should be an agreement of this dimension. So we need to have the same d here multiplied by m, which is the number of dimensions we want to end up with. So when we do this multiplication, then we see that just by looking on the dimensionality of those arrays, we can see that the output will be n by m, because this is what we know by matrix multiplication. This is a property of matrix multiplication. So we started from n by d, and we want an n by m array, an m-dimensional representation of our n samples. So W here defines the projection. So it's the operation we perform on our input data in order to project them to a lower dimensional space. And changing W will change effectively, similar to changing the angle of our hand, will change the properties of this projection. And that means that there are some ways to optimize W based on the properties based on what we want is to keep the expressivity of our data. We want to keep as much information in our data in order to be able to solve different problems. So, and effectively, we can choose different W. Each time we choose a different W, sorry, that's the other way around. We can keep the same projection, and then we can have testing data, as we said before, and project those testing data to our new low-dimensional space. So this follows the idea that we have our data with whatever we do in machine learning, we want to be generalized to new data. So if we find out this projection, we hope that we will put new testing data, and by using the same W, that means that it's going to give us a good projection of this new data. Okay, and this is exactly what we described with Word before. So we said that, okay, we try to project, let's say, our three-dimensional hand into a 2D plane. We turn our hand with relation to the light source, and some of those representations would be good, nice representations, easy to tell that this is a hand, and some other representations would be very difficult to tell that there is a hand. So now try to solve this problem mathematically. And one way to do that is by what is called principal component analysis, which is a method to linearly project a high-dimensional data set into lower dimensions. And in fact is an optimum way, so it's a very powerful technique, linear technique, and is optimum, and that's why it is used. So principal component analysis effectively is a method for us to choose this projection. That would what does it allow us. And it has to find the columns of W, and it can do that iteratively. We can do that iteratively by estimating each of the new dimensions we want. And those new dimensions, in principal component analysis, the goal they have is to maximize the variance we have in our data. Because if you have a high variance in the data, that gives you a lot of information about the data set in that specific dimension. So that means this specific dimension is very important when you try later on to describe your data. If you have a small variance, that means that this dimension, the data, they don't vary so much with it. It's not really expressive. So that's the reason behind choosing then the columns of this projection matrix to maximize the variance we have in the data with respect to that dimension. So another important property of the principal component analysis is that those components are orthogonal components. So once we found the principal component, which is the most important feature where we project our data, then the next one will be orthogonal to the first feature. So orthogonality. And the orthogonality remains even if you have high dimensions. So you can imagine you don't have to have only the 2 dimensions. You can have high dimensional spaces with, you start with thousands of points and you keep 10 or 20 of those dimensions. All those dimensions will be orthogonal to each other. So what does it mean to apply PCA iteratively? So let's start here with an example. Let's start here with a very simple example. So it's only 2 dimensions, so we can describe it. And we want to find those principal components and understand intuitively what those principal components mean. So we would like to turn it to one-dimensional problem. And we try to find the components that they are across the highest variance in our data. And we said also that principal component analysis is a linear method. So that means, effectively, that we try to find the line that would describe our data effectively. And so if we pick some arbitrary W here, and we project the data onto it. So effectively, we project the data onto this line. And we can see the variance of this data, so we can estimate this variance. Then, what we can go is we can go and select the next W, the next option for our projection matrix. And we can now project a point into this component, into this line, and estimate the variance of those points along these components. And we see here that the variance here, the size of the variance, it increases. And we said that's exactly what we try to find with principal component analysis. We try to find components, principal components, that they have the highest variance. So we keep doing that, and then you can see that the highest variance here, it's the one intuitively that goes across those points. So we get a variance much higher than what we had with all the other linear components before. Now, when we project these points into this line, we can now collapse our problem to one-dimensional problem and still keep most of the information we had before. So most of how those points vary across that dimension is described here. So that's the intuition behind the PCA. So we can see that we have encoded some information about our points towards this, the dimension that expresses the highest variance in those points. But we also have lost a bit of information. So if we select this one principal component, I mean, still we lose a bit of information here, which is on the other axis. But it's far less information compared to the one we would lose if we lose the dimension with the highest variance. What we can also see, as I said, that once we select this principal component, we said that the property of the PCA itself is that the next principal component would be orthogonal to that one. So effectively, we can find the next dimension which is orthogonal to this component. And why we want to do that? We want to do that because we want to be able to grasp the information, as much information, which is not correlated to each other. So if we have several dimensions, this is only 2 dimensions, so if we get 2 components, we already described, again we have, if we start with 2 dimensions and end up with 2 dimensions, we haven't really reduced the dimensions of the problem. But if we have multiple dimensions, then most probably you would like to keep the second component as well, and that one would be the one which is orthogonal to the first. So PCA, in fact, okay, we saw that iteratively we can decide which projection to keep. But in fact, it has an analytical solution, and normally we use the analytical solution, and that's well known in linear algebra as eigenvector and eigenvalues of our X, of our input X matrix. Now, in practice, when you have a really high dimensional space, estimating the eigenvalues and eigenvectors directly is a difficult problem. It requires a lot of memory because you have to multiply very large matrices. What alternatively we could do is we could apply what we call SVD decomposition. So we can decompose our input matrices without estimating the covariance matrix of our input array. So we decompose our matrix into components. Sigma is a diagonal matrix, resembles a diagonal matrix that gives us the strength of those components. In order to be able to tell which one is the one which has the highest value, which one is the principal component, which one is the second one with the highest variance, and so on. And VT is the matrix that they give us the components, the vectors in our feature space. So it's what we try effectively to estimate from this problem. These matrices, they have specific properties. So we try to solve a mathematical problem where this decomposition is not a random decomposition. So U by U transpose will give us the identity matrix, and V by V transpose will give us again the identity matrix. You don't need to know the mathematical proof for this problem. So what we said before is the analytical solution depends on the covariance of our input matrix. So to estimate the covariance, we take our input, transpose, multiply it by itself, and that gives us the covariance matrix. But in high-dimensional spaces, it could be difficult to handle this array. So instead of doing that, we can go and decompose X first into three different arrays, as we described before. And we try to estimate the variance based on those arrays. And that's a problem that computationally we can manage easier, and even big companies like Google, they have used it to apply principal component analysis in very large data sets. So going back to our original example, so we said that we had this high-dimensional data. It was gene expressions from patients. There were 3,751 features. We had only 38 patients, 38 samples from healthy and leukemia patients. So we knew that we cannot really build a classifier, a robust classifier, by using all the features. So instead, what we could do is we could use projection techniques. We can use principal component analysis to project those features to 2 dimensions. So now those dimensions is not anymore as independent as before. So it's not as independent as when we do feature selection, where we choose a subset of the original features. Those dimensions, they come from all the features because we try to linearly to fit those points around principal components that describes all the features. So it's a combination of all those features that, but an intuitive combination along the dimension, along the axis, which encodes the highest variance in the data. And again, if we want to decide how many components we want to use, we can apply cross-validation. And remember that we need to apply cross-validation by using, the reason we do the cross-validation is important to use the testing error and not the training error to decide the number of components to select. And again, we can see here with a far less number of dimensions, we can solve the problem far more efficiently. So summarizing, what we learned today is that sometimes we have too many dimensions. And we need to select features from those dimensions. The fact that we have too many dimensions, unfortunately, doesn't translate it to have better models. And we need to select those, and we saw many different ways of selecting those features. So we can select a subset of those features from their original ones, or we can combine our data set and find linear combinations effectively, what we call principal components, that can describe those features more intuitively along the dimension with the highest variance. So effectively, it's like we're taking our problem described in n dimensions, and we try to rotate our system. We describe those data in a system that aligns better with the variance, more intuitively with the variance. And that concludes the lecture about projection. So you could, if you have any questions, please put them on the Mentimeter or just ask. This could be possible as well. So I got a question which is, can you explain more about creating new features from existing features? And that I cannot really imagine it in terms of vector space. Okay, so let's try to think of it in terms of again, the tools we described before. So we said that we start with an array X, which is the number of our samples by our dimensions. And we said that we want to find a way, we want to find an array W, which gonna project our data to a new space, to a new feature space now. And now here our vectors, I assume by vectors in this question where it means the principal is our principal components. So our principal components is what they describe the new dimensions, is the lines we see when we had a cloud of points. We were trying to find the linear relationship, the dimension effectively as a linear relationship of those points. So the principal component in our case were lines across this 2D space where we try to see which of these lines they maximize the variance. Not sure if it answers the question. So this is another question again about PCA. Will PCA be more sensitive to outliers as there might be artificially increased the variance along a particular dimension? Yes, the PCA would be very sensitive to outliers for this reason. So if you have outliers that increases the variance, then that would be a problem. And I guess, as I said before, PCA would be, though, nevertheless, the optimum linear way of projecting those points to lower dimensions. Other ways of doing that are non-linear. So if you have a more complex data set with non-linear relationship, you can use dimensionality techniques which are non-linear, like TSNE and so on, for visualizations. They're not necessarily optimum ways of reducing the dimensionality of your problem. But in certain cases, they can perform well. Okay, we can take more questions later, but for now, I'm gonna go ahead because we still have to cover your use case. I'm gonna go straight. So this is the introductory lecture for the use case about explainability. So there are gonna be 3 use cases and that you will have, and you can choose 2 out of those 3 use cases. So next week will be Dr. K1 with another use case, and the use case is it will give you more context and different angles of solving the problems we discussed during the lectures. So please make your effort to at least submit both of those. The groups must have, are assigned, as far as I know. If you still don't have a group, or there is any problem, email both me and Ali. Ali coordinates that, so he's the person that knows more about it. But in any case, if you, I'm happy to try chase and see if there is any problem. Okay, let's start with this specific use case, and we're going to talk about why we need explainable machine learning. And we're going to see later on how the explainability also links to the feature selection process that we said before. So explainability in machine learning is a very important concept, and the last few years it became even more important because the models became more complex. So if you use, for example, a regression model, that's a relatively simple model, and intuitively you can understand the solutions easier. However, when you get into more complex models, even before you go to deep learning, if you go to random forests, to boost trees and so on, machine learning becomes a black box. And that is problematic when you try to decide to make important decisions based on this black box. So let's consider that you have a patient and you have an output of your model that gives you the risk of this patient with relation to a disease. And you want to use this information to provide feedback to the patient, effectively to even change their medication. So, for example, consider that the input of this model is the BMI, the age, whether the patient smokes, the alcohol, the blood pressure, and so on. So in order to provide this feedback to the patient, we need to know, do we understand why the model came to this output? Do we know the condition and cases that the model is successful and when it is not? So you need to have a confidence on this model, and do we know the factors behind this output? So we have figured out that the age is one of the most important factors, for example, in predicting heart failure. And a large BMI also increases the probability of a heart attack episode. Similar, smoking, it can also increase the probability. So which one of those factors should a doctor prioritize? And if we just have a black box, if we're not able to understand how the model comes to a specific decision, then it's very difficult to translate those models to practice. It's very difficult to apply them. So sometimes, in order to be able to have more confidence in a model, we need extra information about the model. One way to achieve this extra information is if we know, for example, what each node represents. Let's say, similarly, like if we can map in a way our input space to some lower dimension and say, okay, the lower dimensions means whether somebody is stressed or somebody exercises, or whether there is a gender relationship with relation to the risk of the patient, and so on. Then that might give us an intuition about the decision, but we don't always have that. The question is how we can create it. So, as I said before, some of the models are intuitively interpretable. So you get, for example, a decision tree. It is considered one of the simplest models in theory because each of the tree branch, it's exactly one parameter we can understand. So, for example, you can start with the age of the patient, which is one of the most important features we said before, and then decide, okay, based on the age, what is the risk of the patient? Shall I give this medicine or the other? And then you follow along the tree based on the characteristic of the specific patient. You say, yeah, okay, your age is above 60, your BMI is quite high, you're a smoking, you're in a high risk, I will prescribe you this medicine. So it's a very deterministic way of taking your decisions. And therefore we can see here of why some of the models are considered interpretable and why other models are not. So now the problem with the interpretable models, so somebody would say, okay, then why don't stick just to the interpretable models? For a long time we did that, so even now in healthcare, the linear regression, logistic regression is the most common models used. However, they are not the most powerful models. And now that we have more data, we have accumulation of data from patients that become decades long, we have the ability to build far more complex models. With advanced machine learning techniques, you've heard, for example, so far you've done only support vector machines and linear regression, but we can use random forest, or we can use neural networks, deep neural networks, and that will increase the performance of those models. And the reason we want to increase the performance of those models as well is because we cannot apply the model if it's not accurate enough. So we can't say the person, okay, you have 60-40% split between your probability chance to get the disease. I'm going to give you this medicine, especially if you consider the fact that medicines, they have side effects. And somebody would say, yeah, but I mean, I might have 40% split of not getting the disease. Why shall I do this? So you really need to be quite confident that the risk is high. And this confidence needs to be in a model that is well validated and you know that generalizes well to the new data, as we said before. So you need to follow all the principles about cross-validation, evaluate your model, and also estimate the confidence of the model, and so on. But how again, you can go ahead and explain the model to people and consider the other scenarios as well. So not only the clinical scenario, but also in the finance. Let's say you go to in a bank and they have a model to estimate whether you are allowed to get a loan or not. They have responsibility to provide feedback to customers of why their application has been rejected. You can't just reject an application because a model said so. And that's one of another reason that there is a lot of work, the models not to be just powerful, but also to be interpretable and transparent. So we talk about ways, so here this describes the idea about interpretable and explainable models. So we have models that we know that are intuitively interpretable because they are simple enough, like our tree, our decision tree, for example, and other models that they don't have this intrinsic characteristic. Therefore, we need to provide explanations for those. And effectively, we need and those explanations could be the node representations, could be the selection of the features, a selection method, as we're going to see later, could be a way to determine the cause and the effect. Very simplistically, we can map, as I said, the accuracy and interpretability as a two-dimensional graph to explain why we need models that are interpretable. This is just a summary, but I'm going to go to the next part. And I'm going to talk about feature ranking as model agnostic explanation. And we're going to talk about permutation feature importance. So we're going to discuss about one way to achieve that. And this is important because it's one way that you can also use for your use case. There are a few points that we need to make in terms of explainability. And one key idea behind explainability is whether your explanations are local or global. So when we talked earlier and we said that the age is a key factor in predicting heart failure, that explanation, it was actually based on several patient data. So that is our knowledge we have based on several patient data that the age plays a key factor. But it's not it does not necessarily means that for a specific decision, it doesn't tell us necessarily what is going on for a specific patient. So it's important to have explanations which they give us an idea of what is important in the general population. And it's also important to have explanations about the specific decision of the models. And in this case, the method I'm going to describe is going to be a global explanation. So it's not necessarily going to describe a specific decision, but it's going to describe as, you can consider it as another way of selecting important features in your data set. We have also model agnostic versus model specific explanations. Model agnostic is explanations that they don't really require to have knowledge about the model. So that means you can the algorithm, you can change the model, you still apply the same algorithm. If it's a model-specific explanation, then this is a specific technique for this particular family of models. So you have, because it relies on specific properties of this model. So for example, if you do deep neural networks, if you visualize the layers, is a way to explain the features. That's specific to that way of modeling, because you don't have layers if you do, for example, support vector machines or random forest. We can have also data modality specific versus data modality agnostic, but we're not going to go into that. And we're going to have ad hoc and post hoc explanations. So post hoc explanation is if you train a model already and you give the model to the others, and then you want an explanation afterwards ad hoc if you try to incorporate that. So we said about global explanations already. So we said about data exploration and global importance. So we're going to go for model agnostic approaches. So we have model flexibility. You can change the model. Now we don't have to stick to one model. Explanation flexibility, representation flexibility. We're going to talk about some also local interpretable model agnostic explanations, but we're going to do that to the next lecture. So now for this one, I'm going to focus on permutation feature importance. So the permutation feature importance is quite of a powerful method. It's a relatively simple method compared to other ways we use for explanations. And the reason I chose that it's because it's powerful and it's especially useful for nonlinear or black box estimators. So we don't need to worry about which model we have selected. It can apply on different models. And the way the permutation feature importance works is by trying to break the relation between the feature and the target. So we talked before about, in a way, when we talk about selecting features, we say, okay, we want features that discriminate the two classes, and we estimated the significance of those features based on how they discriminate those clusters. So this is one way of telling the importance of a feature, and this importance gives you an idea of whether to include the feature or not. The permutation feature importance method has some similarities because by breaking one of those features, you can go and look at the classification performance. So you look into the classification performance, and then you can decide, based on the classification performance, as we're going to see later, how to rank those features. So you say, okay, I will break this feature, I will corrupt this feature, so the model won't have information from this feature. Would that affect the result? If it affects the result, that means it's an important feature. Now, why it's different than the previous technique? Why we don't just go and look again those nice distributions we did before and decide? So remember here that we have models that we have already trained based on a specific number of features. So we don't try to solve the problem of high dimensionality, of the curse of the dimensionality. Here we try to explain the model we have already. So we have a model built already based on our 15 features, and we want to know which features are the most important. So we try to solve a different problem. And how the permutation feature importance then work? So as I said, we have here our model and our data set. And we want to compute a reference score, S, which reflects the significance of the model on the data. And also, this score can be, for example, the accuracy of the classifier, but you can also consider it can be also a score which shows the importance of your regression model, for example, the R-squared. So what we do now is for each feature, we have trained our model with, and for each iteration, we go and we randomly shuffle the column of this feature. And if you randomly shuffle the column of your feature, that generates a corrupted version of your feature. So you scramble all the information, and you put it back to the model. So basically, your feature is useless now. And we can use that to compute the new score of the model on this corrupted data. And we do that iteratively for each feature. That will give us the importance of this, the relatively importance of this feature. So that's the intuition behind how to understand which of the input variables you have, they affect most the output. So if you say, for example, to a person that comes to ask for a loan that your application is rejected, then you can tell them, okay, the main reason has been rejected is, for example, your credit history, because the model output that as the most important, and then all these other factors, X, Y, Z, following. This is a similar algorithm that allows you, it's again the permutation feature importance algorithm that just with the variance estimation here. And remember that you don't need to retrain the model. So that's the important bit here, that you don't need to retrain the model again to get what is the important feature out of your model. So it has some advantages that is simple and can give us, it reminds us the feature selection we've seen before, but it has also disadvantages, and one of the most important disadvantages is with relation to the interaction between features. And we're gonna talk about that also in our next lecture. But effectively remember that if you have two features correlated to each other, they can be both of those features are important, may be important for the model. If you remove one of those features, that means that will not necessarily reduce the performance of the model, because the model will recover the information from the correlated feature. So remember that the PFI is a powerful way, is a good approximation, but again, if you have correlated feature, that's not good enough. And let's go and see also a bit more specific about the exercise you have to do. Just try to understand a little bit. So the exercise has been released on Moodle, and it does include a file where you can use it for the pre-processing. We don't want you to waste your time trying to understand the data. We want to spend your time trying to develop the methods in order to explain your models. So we want you to spend time making your models, training your models, and explaining your models. In order to understand here the use case, to give you a bit of context of the data you're going to use. So we're going to use ECG electrocardiograms. It's data that doctors use to examine the heart. It's quite powerful methods because people can use those devices at home as well. Certain abnormalities, they're not present all the time. So doctors, they can review those data sets from home. And they give you, they can be multidimensional because they have a lot of channels, so it's spatiotemporal signals. They have both temporal and spatial dimension. And for this reason, they give you a good idea of how healthy the cardiac cycle is. So each abnormality on your ECG can relate to a specific abnormality on the cardiac cycle. And that's that's the reason a lot of times doctors, they segment the ECGs to different segments. So you have this very distinctive figure of QRS where most of us recognize, even though that we're not doctors. So we have an idea, okay, that's an ECG. We've seen it so many times on TV. You have a segment and with a specific morphology for healthy people, which we call PR interval, a segment of ECG, and a segment after the QRS, which you call a ST segment. So they have specific morphology, and based on the morphology, doctors, they can decide not only that there is an abnormality, but where the abnormality is, so they can get a good idea. So manual ECG analysis is very time-consuming. Normally they follow the patients for 24 hours, 48 hours, sometimes more. So there is no way that the doctor would go and sit there, and even if they have the best intentions, it's not certain that they will be able to examine that properly. So we do need ways to help them. And machine learning has been extensively applied in this type of classification. The ECGs are susceptible to noise and so on, and this is just to explain that some of the preprocessing is about removing artifacts, motion artifacts, and that they can arise from the motion of the patients, but also on the fact that some of the electrodes might be misplaced. Some of the machine learning models, they can cope better than others with relation to the noise, but the traditional machine learning models, they are limited most of the times. The data set you're going to use is an open access data set. Is well-known data set, is one, if most probably the only data set that has classification per bit. So what that means